HVAC systems, primarily the ventilation and exhaust side of things. So we did a talk here 2016, Greg and I jointly, and the focus there was the building enclosure and mechanical heating and cooling systems. Today, with a focus on healthy homes, we're looking at sort of the air side of it. So I'll talk a bit about heating and cooling because it all sort of ties in, but there's not as much of a focus there. So we do work across Ontario. We've got offices in Cambridge, which Greg heads up, and then Cobourg, Ontario, where I'm based out of. And we do sort of two pieces of things, the building side and the renewable side. So I do probably 70% on the renewable side, 30% on the building side. Greg has a sort of a flip switch. So we really try to cross-train our staff on both aspects. And what's really exciting is the projects we're working on now are net zero. We're doing the mechanical design, we're doing the energy efficiency. So it's really bringing all those different pieces together. So it's been really exciting the last few years, both in terms of projects, but also systems and technologies, and what the manufacturers are putting out. It's a pretty interesting time to be in this business. What's interesting to note here is the vast majority of systems that go in are air-based systems, and that question came up. I forget who that was from, but about radiant heating and cooling systems. That changes the equation quite a bit, and I think what we're going to be talking about primarily would be applicable to both in terms of doing a dedicated ventilation system, but I'll unpack a little bit what that looks like. The dedicated system is what you're going to see for any project that you've got radiantly heated or cooled. How many people here live in a forced air house, have a furnace? Okay, keep your hands up. How many people are designing houses with forced air? Okay, so it's like, it happens. There's projects. I think a lot of it depends on budgets. A lot of it depends on do you want cooling? So who here is designing with cooling in all their houses? Okay. I think, and Andy did a good job addressing that. We have the benefit, I think, of the projects that we work on where they are in great surroundings. They do have space. When you pack houses in, it changes the entire microclimate of that area, and so it starts to change what that demand is. Most of the time we run into challenges with, if cooling is required, is all of a sudden a radiant system and a ventilation system and a heating and cooling system. You've got a whole bunch of systems, and when that goes out to tender, the prices come in high and everybody's wondering, how did we arrive there? So I think, anyways, we'll talk a bit about, sort of the impact of that, but a dedicated system gives you that ventilation where you need it. You end up with more ducts, you end up with, a parallel system sometimes, but it's the easiest to control and the easiest to balance. Pros and cons, so in terms of forced air, integrating with forced air systems, it's often more cost effective because you're really running ductwork for it. And the biggest trade-off that you end up with, I think the next picture shows that well, you have a single system, you can turn off portions of it, but if you don't have an ability to dial back the fan, you end up with the cycling, you end up with sort of incomplete ventilation. So what often gets done in conventional houses, they end up adding the HRV or ERV, and they integrate it with it. Now the biggest issue that we see in terms of doing that is whether you're running that fan, how do you balance it? And in current projects that we're seeing, the loads get so low that it's very hard to do that effectively. We have a problem right now that we can't even find. Well, what happens actually most of the time is the furnace fan shuts off and you don't get any air distributed. Right? Yeah. So there's a few cases. We've got some projects where we're tying it in on the supply side, so we're not relying exclusively on that fan. But then you've got a risk of it being, especially if it's not a super efficient HRV or ERV, it being a lot colder and having that air. Also, it's very hard to distribute through that, oversized ductwork. So it's either way. Yeah. Speaking, we try to decouple those systems. I think historically it was done because of these cost efficiencies, but it's no longer that. And I think especially if you're looking at, if you are interested in radiant systems and you don't need to have cooling, then it's a natural way to, to move towards. Just a couple of things before we dive into the ERV side of it. So regardless of whether you're coupling in with your ventilation or your heating and cooling system or decoupling it, the big thing is about the movement from HRVs to ERVs, and Andy did a good job of going over that. We pretty much, at this point, aren't seeing many HRVs going in. There are applications, there's conditions where it makes sense, But most of the time we're dealing with the ERVs at this point, and trying to really figure out the most effective way to integrate it. Yep.
Could you maybe just explain the difference between the two? Some people are asking me at lunch, like, what are those two things that mean? So,
Sure, yeah, no, for sure. So basically, in an HRV, it's a heat recovery ventilator. It's only transferring heat. So it's a heat exchanger. I'm trying to see if we've got a cross flow here. No.
Two sets of straws.
Yeah, so basically you're passing the air through, and the only thing transferring between the outgoing warm air and the incoming cold air is heat. In an energy, you've also got, you're moving that moisture through, whether it's with a wheel, which on larger case, or what we deal with in the residential scale is a core, and that core is able to pass that moisture through. And so, as we talked about in terms of sensible and latent loads, in terms of trying to get rid of the humidity out of the space, you're cooling in the summertime, you're taking that humidity out, and then you're bringing this humid, warm air back into your house. And so if you've got an ERV, you can take that moisture, dump it into the outgoing stream, and you get that added benefit from it. Historically, it didn't seem like it made sense to do in our climate, but as you start looking at how the house is operating and what else is happening within the in the house, it has a huge benefit. I think the other key thing is that the technology has really improved. I will throw some names up here because I think it's important to understand what the costs and stuff look like. But you know, the technology has improved where you can get energy recovery technology in a smaller size, and the costs don't have to be crazy. And I think, you know, again, Andy talked about efficiency. What he didn't say when he was talking about the fan power is that fan power is electrical. Your heating's generally not always electrically driven alone. So it's actually a bigger, you know, bigger issue to factor in. Yeah, it's, anyways, that efficiency piece is an important one, and the humidity is also a key piece. Now, when people talk about efficiency, they're often talking about just the nameplate efficiency. And why, you know, we're talking about this today is because in dealing with a house and home and pollutant source, trying to figure out how the system's actually going to operate. And one of the biggest issues that we run into in our climate is when an HRV or ERV goes into a defrost mode. And so what that means is the core drops in temperature. You get what they call a freezing event, and you've got to have somehow thaw out that core. And so the most common way that they do that is to recirculate. And so they basically take indoor air, and instead of exhausting it, they run it back into the house. And so most systems are pulling your exhaust air out of your washroom, out of your bathroom, your kitchen. You're pulling that back in and then sending it back through into the house. And so, you know, in that condition, you know, it's a pretty big issue that you can run into in terms of trying to get those pollutants out. Couple of options we'll look at. The other option is to preheat the incoming air and create, you know, avoid that sort of challenge. So on here we've got freezing events occurring, you know, down around 10 degrees F. Again, it's going to depend on how quickly the supplier, because there's going to be a certain thermal mass in terms of the ERV itself. But it's going to switch it out, start recirculating, and in some cases cycle between. So once it reaches temperature again, the bypass damper kicks back, and it'll bring outdoor air.
But that's at like -5, -7 Celsius, right?
That's right.
That's happening.
Yeah, so it happens pretty quickly, potentially. Yeah. It also depends on how balanced you're running and how much exhaust you're pushing out through it as well. So in this case, yeah, your benefit is that you're taking some heating load off the system. It's in a recirculating configuration. It's pretty commonly set up within the ERVs and HRVs. The drawback is that your continuous ventilation in your airtight house is now discontinuous, and it's stopping, and it can stop for, you know, 20, 30, 40 minutes out of every hour, depending how long it takes for it to warm itself back up. And as we talked about, recirculating back into the airspace. So the other option that we're seeing put in is sort of a preheat. And so this is done a few different ways, but basically the idea is you keep your ERV running and you introduce heat upstream so that there's not cold air being introduced into the heat recovery ventilator. The challenge here is how you do that. There's an energy penalty and the cost to integrate it, but there's a few different options. One of those is just a preheat system. The cheapest, first cost-wise, not necessarily operating, is electric duct heater, so to be able to preheat that air. Again, you're looking at how often does this condition happen. It may not be enough that it's going to drive up your overall heating. If you've got a hydronic system already, you can do the same thing with a duct heater, but with a hydronic loop to provide for it. And again, then whatever you're driving that source, whether it's wood-fired or gas-fired or a water source, heat pump, geothermal loop, you can use that preheat. Another option that's been used more often, especially with Zender ultra high efficiency ERV, and there's also some off-brand products too, is to do kind of an indirect geo exchange. So instead of having a heat pump, there's pipes that are put in along the foundation, or in this case, sub-slab, and there's a brine loop that's circulating and pulling that, that cooler or the warmer energy from below the house, and using that to just step up the temperature before it hits the ERV. And that's, higher first cost, obviously better cost-wise than dealing with electricity for preheat, but there's some added complexity. You've got a pump to run, and I think there's more study that needs to happen there. You're getting this benefit, you're running a pump, depending if it's a variable speed pump, how fast it's running, how much electricity that's taking needs to be factored into it as well. So this works a lot better if you've already got, some sort of radiant type system or geothermal where you might have extra heat. So that's sort of the technology we've had for the last number of years. The last few years we've seen a new sort of version of the ERV come out, and that's a heat pump based ERV. And so what that's doing is it's actually taking and extracting that heat from one airstream into the other using heat pump technology, which allows it to run at more extreme temperatures. There's some limitations in terms of its cold weather performance in terms of going to like a cold climate heat pump. But what it can do is actually bring in quite a bit of new opportunities where you can do more with the same unit. So on a really ultra low load dwellings, we're doing some, Greg mentioned about the multi-unit residential. At some point, these can become your heating and cooling system. So the unit on the top, Minotaur, again, it's a relatively new technology, but it can do heating, it can do cooling, it can do dehumidification, it can do your air exchange, and all in one package. So we're doing sort of a comparison right now for a project where the Minotaur on the right-hand side there with a duct heater just for backup, because it doesn't do well once you get below -10 Celsius, compared to all this other equipment. So the other equipment that you have is a heat pump, variable refrigerant flow. You've got a baseboard heater for some of the perimeter spaces that don't have the distribution. You got a dehumidifier, humidifier, and then the one second from the bottom is a transfer fan, plus your ERV. And so they're bringing all these pieces into one. Now there's benefits there if you get your loads down, but there's also, and the biggest challenge is the risk factor. So now you have one unit that if you've got a failure issue, you've got a bit of a challenge to deal with. But from a cost perspective, believe it or not, the capital cost is higher on the right-hand side, the integrated one. But from a labor perspective, it's a night and day difference. Right, so if you've got low enough loads, so if you're doing like a passive house level, in this case it's multifamily, so you've got a bunch of demising walls that are shared, they don't need anything extra. The duct heater steps it up, and that's sufficient. So, but again, it depends on how far you can get those loads down. It doesn't work well as a retrofit unless you've got the space to run it, right? That's one challenge we have. So we're looking at doing sort of a common header where we're picking up multiple of these units to be fed, because it is, there is more ductwork. You lose some ceiling height to be able to deal with it. But so that's one piece. The other piece is just in terms of servicing and parts and being able to deal with it. It's sort of a one-stop shop. So a few code challenges, I guess, with ERVs. OBC requires them to have a 55% sensible heat recovery. When you look at sort of the ratings and you look at the defrost cycle, that sort of nominal efficiency, so for example up here, sensible of 80%, total heat recovery can be down to 57%. So your mileage will vary. I think when you're comparing different products, it's really important to understand what temperature it goes into a defrost cycle, and how that defrost cycle is going to impact your energy consumption. We have a challenge. A lot of, like, Ultimaire is a good example. They've got a great product, but the way their unit operates, any waste heat from the motors gets dumped into your airstream, so it becomes part of your, takes some of the heating load off. But it's not well set up for our test standards. So every time we do use one of those, we've got to go through an alternatives compliance path for it. So they're not doing, and then the heat pump ERVs are even more complicated to sort of get through. So I think the codes are trying to catch up. I think there's a lot of opportunity, with some of that, with the manufacturers. And to me, it's just interesting how quickly some of that has changed. The other thing that we're seeing, and this is interesting because we've seen this on the commercial side, and it's starting to sort of move into the residential side, is demand-controlled ventilation. So looking at how you control the amount of ventilation being supplied, so and modulating it basically. So CO2 is being used as a proxy for people, usually controlling anywhere from 250 to 450 parts per million. Sometimes people confuse that with carbon monoxide. Carbon dioxide, you need, before you start to get really sleepy, it's like 25,000 parts per million. So it's really just being used as a proxy. We're often actually, in a lot of projects, using occupancy sensors instead of CO2 sensors. Just same idea. Okay, you've got somebody in there, you bump up your ventilation flow rates to deal with the people. Andy talked a bit about variable speed, but essentially you can do that whether it's an ECM motor or just having different stages to step up how much ventilation you need within the house. Most of the time your ERV is going to be equipped with some kind of bypass or override anyways. So if you're having a shower, you get increased loading, you can step up. So this is just one way to make that a bit more seamless. People don't have to think about it as much, but introduces another, another factor. So the other piece of the equation, and with these ducted systems, is the exhaust side of the equation. One of the, I guess, lessons learned we've seen over the last couple of years, which Andy talked about, but we're seeing in terms of trying to deal with it, is the kitchen range. A lot of people, especially if they're doing higher end houses, want a gas range to cook off of, and you can do a lot of work to make the enclosure good. And you put a gas range in and it changes the entire balance and changes your entire mechanical strategy. So that's the first thing. So if you've got somebody who's committed to zero combustion, that's great. And then the second part of the question is recirculating or not. And we'll look at a few different scenarios. Other factors we run into: dryers. Will we be using a heat pump dryer? Are we going to be exhausting with that dryer? Wood stoves. So wood stoves and fireplaces introduce a whole other dynamic in terms of providing combustion air, where you provide that air, how that's provided, what that does to your overall enclosure. It's kind of amazing how much air we lose through chimneys in that kind of condition. Toilets, composting toilets, are they going to be used? Conventional toilets, is there a fan? Do we have to have power run to that? Does that have to run continuously? What does that look like? And then other pets I added that pets one after Andy's thing, but pets, records. We have a project where the storage room, we never put an exhaust vent in it. It's being used to store records. You open it up, it's being used to store records, and it's a good example where it'd be good to understand what the requirements are. Filtration. So I won't talk too much into sort of ultrafine particles and some of the risk factors there, but a lot of commercial projects move to this MERV 13, which is sort of the highest equivalency you can easily purchase. But we're starting to see residential projects move in that way as well, and looking at what they're drawing out. One of the things that I think is an important understanding and trade-off is that ventilation for good indoor air quality is often in direct competition with energy savings. So, Andy talked about if everybody worried about comfort, we'd save energy. The reason that is because you increase the enclosure performance. But in reality, the fact that we have to provide ventilation and how we do that is always an energy penalty. So there's going to be a trade-off there. So something like demand-controlled ventilation, you want to adjust that ventilation rate down to only supply what you need to. At the same thing, you can over-filter, right? And depending on what the profile is and how you approach it, you can pay quite a big energy penalty, to the point, like on some projects we've seen a 30% fan power premium just for going to a MERV 13 filtration. So filters are good, but it's important to understand what you need and how much you need to be able to do that. And how high of a level do you think you need? Burning fireplaces, wood stoves. So again, providing combustion air for it. The biggest issue is sort of creating an imbalance. So if there isn't, Andy talked about having an interlock with a vent or some kind of damper. But if you don't have a makeup air, basically what starts happening is it starts drawing everything through the combustion. And so odors, smells, the kitchen, everything will just start getting sucked through there. And it creates a pretty uncomfortable but also risky situation in terms of how it's going to operate. Cooking contaminants, so basically range choice affects what you're going to be dealing with. Electric isn't super clean either. Gas is worse, there's more coming off of it. But electric, you still get the risk of ultrafine particles, and then food itself, water, grease, whatever you're pulling off. So the big debate that we end up with on every project, it seems, is what type of range hood to use. We haven't seen a lot of induction out there. We're seeing more of that. I think anytime you get, that kind of surface temperature, there's still that risk. And at that point, it's, but yeah, there's definitely some efficiencies there. We've done some testing with induction on backup generator systems and off-grid systems just to see. It's still, it's a hard trade-off. People say, oh, we've gone off-grid, and then you look in the back and there's a propane generator. And so it's, trying to figure out a way to go fully electric is an interesting challenge. And that's, that's one way to approach it. You still need to have ventilation or some sort of exhaust. And I think the biggest issue is the range hood, the type. So the main two solutions are a ducted strategy or a ductless and recirculating. So the ductless recirculating, the most common is that one that sits under your microwave and blows a bunch of air in your face when you're cooking. May have a charcoal filter, may not. Generally has some kind of aluminum grease filter, but doesn't. There's better technologies, but it gets you an idea of what you're dealing with. Looking at the dimensions and the configuration of your range hood, where it's placed, even how you cook with your range. Like my wife and I always cook towards the back because we've got young kids. So you always worry about them grabbing something. I recently had one of my outlets in my stove start arcing for no reason. So I took it apart to see why, and it was a manufacturing issue. Something got in there, some moisture, something. But what we noticed is that all the wires, everything in the back, I think probably 95% of the time we use the back elements, were starting to wear. And it was kind of concerning, So working towards the back, you might line up better with your venting. But how you cook, what you cook, if you are used to cooking with gas, all these are important things to understand, especially when you're planning an initial design. So, according to Andy's numbers, our numbers are low here, but we often see that the bigger the range hood, the more sump there is, and how much overlap is going to perform better. Similar to what Andy saw, we don't need to have massive amounts of CFM to be able to withdraw it, but it's all in the geometry of it and how you use it. There are some design guidelines out there for that. The code's not as prescriptive on it as it could be. So it's that's why you often see, it usually comes proud a bit of your cabinetry up top, but to be really effective, it's got to be more like a commercial scale where it covers everything. And then you've got interaction, exactly. The biggest issue that we run into is so if you've got this, and it depends how it's running, this is directly vented out, and you can't put this air through your heat recovery or your energy recovery. And so you end up with this energy penalty of this exhausting out. And so the makeup air is great for balancing it, but from an energy perspective, it becomes a pretty massive part. And as we mentioned a few times, as you start to drive down those loads in the building, I mean, we have commercial or residential projects where of the energy use, 43% is ventilation related, and 43% is domestic, or 45% is domestic hot water. So the ventilation piece becomes, a pretty key factor, both in terms of how to run the building, but also, the installed capital costs to do that. So a method that we've been looking at, or we've used quite often, and again, it depends on the developer, depends on the owner, what they're willing to accept, but is a recirculating range hood with integral carbon filter, so you get that filtration. Disposable grease filters that you replace depending how often you're cooking and how much they load up. And then doing a takeoff for your ear via general exhaust from the kitchen. So keeping it away from the stove or where the grease-laden vapors might be coming up, and being able to exhaust that so you don't basically contaminate your core. Different options for recirculating range hoods. I mean, there's all sorts of configurations. The old school way was always just dump it out the front, so suck it up, dump it out the front. Now we've got some that are, creating a separate circulation loop and then sending it up and getting it up higher into the space. Again, for us, it's a matter of figuring out where that's flowing and then figuring out what's the most efficient way to exhaust that room and sort of bring that air out from there. We're finding for the most part, and there needs to be definitely, Stu wanted me to underscore that, there needs to be more studies done for this, but we're definitely seeing that this is the more effective way, I guess, to balance the energy needs with the exhaust needs. But as soon as you've got anything special, and I think it's really important to understand how the user's going to use that kitchen. If you've got somebody that cooks a lot, that wants gas, do a direct vent and figure out other ways to, more efficiently make up that heat, because the worst thing is to have a mismatch between the user and how they're going to use that space and what you're providing within it. A lot of projects we're doing right now are seniors living and low-income housing projects, and it's an interesting discussion to have, like, how much are people going to be cooking, how often they can be cooking. We get into big debates about that, how much water they run to wash dishes. Is it a 5-inch deep sink? Is it a 6-inch deep sink? All these things add into it, and I think the big thing is making your assumptions reasonable, right? Check in with what your client, your user group, you might not know the end user, but hopefully the people you're working with have a good sense of that, and then making sure there's an understanding with the users on what those assumptions were, because that can wildly change how it actually operates. When you get into multi-unit residential and you move to actually 62.1 standard, you're treated as a commercial space, and so what happens is there's two components to ventilation. There's the floor area, which is based on anything that off-gases, any contaminants, anything. There's a base minimum amount that you've got to keep the ventilation running versus the people portion. And so depending on the space type, that ratio can be quite dramatic, like quite a big difference. So in that kind of facility, depending on how it's been interpreted, they might just have a base load exhaust and ventilation that they run all the time, which would be that fan. In a single family residential, it's more often you see that it can get turned right off, and so you don't have that. But that's really, it depends on the code. The other issue that we run into on, high-rise type developments is they start ganging up exhaust stacks and ventilation stacks, even newer ones, and you start to get issues with stack effect and just it pulling air between floors. And so that's another strategy that we use, is to try to use recirculating range hoods, or at the very least compartmentalize it on a floor-by-floor level, so that you're going exhaust and makeup is coming in at the same pressure differential within the building. Dryers, here's another great one to get into debate about. So most dryers are direct vent, right? It dumps the air out. There's some really interesting European products that are condensing dryers or heat pump based dryers, and so you're not directly venting. I don't have one of these yet, and I don't have one because I don't think my wife would be patient enough. Like, it takes a very long time to dry a load of laundry. What's interesting though is it keeps all that heat that you're just venting out with a direct vent in your space, right? So all those gains offset your heating load through the winter.
What about the humidity?
It stays there too, right? That's the challenge. So it's it depends. If you heat with wood and you need some extra humidity in the winter, that can be great. If not, it's a big problem. Yeah. So, and also again, a question on how often is this going to be used, right?
Right. Yeah.
So we're seeing them used in some of the senior living projects because it doesn't take up much space. You can have the same unit be your washer dryer and do everything, right? Again, this is maybe the public service announcement piece of it. So Greg did some work with the City of Guelph on developing a radon awareness program, and I think this is Stats Canada information. I mean, if you look here, Ontario's low. You know, you just pat yourself on the back. You know, it's not so much of a problem.
We're just lucky.
It is a problem, and it's you know, it's the second leading cause of lung cancer in Canada after smoking. Right, so 16% of people who have lung cancer have it from radon, and it's a micro. Like, you could have a house here that has it terribly, you have a house down here that doesn't, and so yeah.
Yeah, just to make that clear.
Don't rely on the map. Just get it tested. They're not expensive. You can. The solution's sort of like a range hood. So there's retrofit options there for new construction. What you end up doing is you want to try to get a subsurface, like below the slab sump, so you've got your vapor barrier and you're pulling that out from underneath and venting it up. I mean, this is sort of a retrofit. You see it's got the booster fan outside. They do that because if there's any leakage around the fan, it's not in your house. You can do this passively if you've got new construction and you can plan it out so it's not stuck on the side of your house. But do the readings, and it really comes into, especially if you've got an older house where there's a lot of cracks in the foundation, there's sump, pump, pits, any sort of openings, that's where you're going to see more, you know, more issues. To put in that, you know, 4-inch ABS or PVC pipe, you know, plus tying it in, I mean, there's a bit of planning in terms of how you do your sub-slab work, but yeah, it's good practice. I mean, it's like any other contaminant. It's going to move to those spaces that have poor circulation, poor air. It's going to collect, I should say. So yeah, if you've got an existing basement, you're not going to rip up the floor slab to put this in, but you're going to move that air. You're going to exhaust that out. I won't get into products on this, but there's a ton of new apps and software and products available for indoor air quality monitoring. Some might even argue to a fault. Like, we can probably start getting really scared about things that aren't, you know, a major issue. But I think awareness is always the best. So I think it's a, you know, it's a good strategy. Understand it. You know, we were putting this presentation together. My wife said, you know, you're sort of like the shoemaker's kid who has no shoes. Like, my ventilation system's in a box. I got to put it in yet. My house is leaky enough that it hasn't mattered yet. But it is important to, you know, to appreciate, you know, what it is, measure it, and see. Okay, so this, Stuart and Greg both said to me, I have to say this. Just because you have a passive house doesn't mean you don't need a mechanical system. So it's really important to think about it. And I think, you know, some of the unintended consequences of going to that level, what we're seeing now are we can't get heat pumps that are small enough to serve properly. We're seeing some changes, some improvements. Citrix has a water source, or Childrix has a water source heat pump now that goes down to 1/4 ton. Before that, we were kind of stuck at 3/4 of a ton. So very small units and zoning, you know, it starts to play. But it's very, very important to have your expectations set right in terms of what your mechanical system needs to do for you, and understand the things. Like, most of the time you should never be thinking about your mechanical system when you're in a house unless there's a problem. And that's one of the biggest challenges for HVAC engineers, is that we only hear about it when there's a problem. So if they're doing their job right, it should be a comfortable space, it should be well ventilated, it should be a healthy space. But it does need to be there. It doesn't happen passively. So that's my last point. Any other questions, or
How do you feel about
on the living wall thing?
Yeah.
So mixed, and the reason is I haven't seen it implemented well. Right? I think, you know, the theories there, like some of the work that Alan Darlington's done at University of Guelph and the testing, you know, from a TVOC perspective in removing those contaminants, great. You know, I think there's a good opportunity. The problem that I see is that when it's implemented, again, my experience with living walls is primarily all commercial projects, it gets value engineered down. And so it's not properly planned out with the mechanical system. There are risks associated with mold formation and, you know, the increased moisture loading. So I think theoretically it's great. I think applications and how we've seen it implemented is problematic. So it's, I mean, there's great examples. I'm sure anyone can come up with good examples of where it's worked. The ones we end up seeing are problems generally. So the same sort of thing, I didn't talk about it, probably should have, but earth tubes as a ventilation strategy. So as a preheat, you know, putting a, or pre-cool, sorry, putting it in a pipe, pulling your air in for your ERV, preconditioning it, whether it's a summertime or winter time, right, to avoid that frost cycle. Again, the challenge is, keeping that pipe dry and not getting any sort of mold formation in it, right? And that's a hard, because that's not a conditioned space. That's where we've seen brine loops being more often used, so that you don't introduce that that level. You can do it. There's ways to do it, but it can be a challenge. So
Great.
good.
Awesome. Well, thank you, George.
Okay.